So in this example, you have 1.5 grams of C6H6, and it's going to go through combustion in what's called a constant volume calorimeter. There's a temperature rise in the calorimeter of 2.7 degrees Celsius, and the calorimeter has a heat capacity of 23.24 kilojoules per degree Celsius. Calculate the molar energy of reaction. So let's talk about this for a moment. Constant volume calorimeter is also known as a bomb calorimeter, which is used experimentally to measure the heat of a reaction. So basically, you have a reaction like this combustion reaction occur in a chamber, and the chamber itself is a calorimeter. And so the heat that's given off from the reaction gets absorbed by the calorimeter. And so there's an exchange where the reaction loses heat or gives off heat, and the calorimeter absorbs the heat. So you end up with a scenario of the negative Q of the reaction is equal to the positive Q of the calorimeter. Okay, so at constant volume, that means that work is equal to 0. So in other words, this container is not going to expand or contract, so it's not going to do any work. Well, if we recall the equation, delta E, and we're going to put of reaction, is equal to Q plus W, and again, these are all going to be of reaction. Well, W equals 0, so it's not doing any work. Therefore, the delta E, or the energy of the reaction, is going to be equal to the Q. And this is always going to be true, that at constant volume, E is equal to Q, or delta E is equal to Q. So with this in mind, the delta E of the reaction is going to be equal to, and notice that the Q of reaction is the same as this guy right here. So, and let me go ahead and change my signs. I'm going to make this one positive on this side and make that one negative. Because it really doesn't matter the signs, it's just showing that there's a balance in the heat exchange, that one loses and one gains. So, if I were to replace this for my Q of reaction, I would get delta E of the reaction is equal to the negative Q of the calorimeter. So, there's an equation for the calorimeter. The Q of the calorimeter is equal to C delta T. So I'm going to go ahead and insert this in place of this, which is going to give me the following equation. Delta E is equal to, I've got my negative value there, negative, and I'm going to plug this in for my Q calorimeter, C delta T. Okay, so it kind of took a lot of work to get to this equation, but this is going to be the equation that we can use to solve for this. So pretty much if you're dealing with a bomb calorimeter at constant volume, then this will be the equation that you could use to solve for the molar energy of the reaction through this. All right, here's the equation that we came up with, that the energy of the reaction is going to be equal to the heat capacity of the calorimeter times the change in temperature of the calorimeter. So when we plug in these numbers, so there's the heat capacity of the calorimeter, 23.24 kilojoules per Celsius, times, and the temperature rise was 2.7 degrees, and that gets us this amount of energy. Keep in mind that this amount of energy is based on, right here, 1.5 grams of reactant. So the question is asking, what is the molar energy or amount of energy per mole? Right now we know the amount of energy per 1.5 grams. So what we'll do is we'll take the energy, which is negative 62.74 kilojoules, and we're going to divide that by the total moles. What we are given is that 1.5 grams of C6H6, and if I want to change that to moles, I'll divide by its molar mass on the periodic table, which is equal to 78.12 grams. So taking the 1.5 and dividing by the molar mass of C6H6 is going to give me the moles. And when I take this value divided by that value, I'll have the kilojoules per mole, which is going to be negative 3,267 kilojoules per mole. And so this is the molar energy of this reaction.